can start. So welcome everyone to the second lecture of this course on random matrices and universality. Last time, I think the last thing I showed you was we were looking at this rescaled k-point correlation functions, and I claimed last time I had an E fixed between -2 and 2, then I had this rescaled correlation function, and then I claimed that this converges to this sine kernel locally uniformly. So I hope you're all more or less familiar with the notation. If something is unclear, just ask me. Maybe the interesting thing here to note is this the structure of the sine kernel. So that's the determinant of k hat alpha I alpha j. And k had this was the sine kernel, so sine of phi alpha minus beta divided by pi alpha minus beta. And what we want to do, or what I will do today, is I'll give you some vague idea, or some idea of how to prove it. Last time we proved the case when E was 0, and then we had to use this Laplace method. But here we will see that when the E is non-zero, it becomes much more complicated. And I'll indicate what's the problem and how one can circumvent this. And then after that, I will start motivating a bit what we'll do in the rest of the semester, give you some short introduction, and then start working towards universality and going this direction. Okay, so let's start with the idea of the proof here. And well, maybe I call this star. And last time the idea was that we can rewrite this. Maybe I should not quite recall all of the notation, but maybe at least some. What is a good way of doing that? So yeah, so maybe I just here as a small recollection. So we had this rho n e k hat, which had k arguments, and that was defined as there's the usual correlation function, but with some non-trivial scaling, which gives you exactly the way to go to the local scale, and so on. And then there were some Gaussian weights, times product Gaussian weights. And then this rho n, we knew that this was expressed as the determinant of k hen evaluated at certain points, right? And then via using these orthogonal polynomials and these things, we could express the kn. This is a combination of these Hermite polynomials. So there were the Pn. What was it? I just want to schematically recall what the structure was. So yeah, there was a Pn minus 1 minus Pn minus 1 Pn. So in some sense, well, there was an xy here. divided by x minus y, and there was some there was some coefficient here which I don't want to write out. So the main point is that this is a function of the Hermite polynomials, and then to study the Hermite polynomials we use this trick with the Fourier transform. So we wrote the Pn of x, which is minus 1 to the n e to the x squared dxk e to the minus x squared over 2. We wrote this in terms of the Fourier transform, so this was so this finally looked like this. This factor remains, the minus 1 goes away with the derivative, and there was some coefficient here, which is just the normalization of the Fourier transform. Okay, so this looked like that, and then for x we basically had this here when e is equal to 0. So in particular this this other coefficient did not matter, but now we have to watch out because now we will get the complex argument because the e here is non-zero. Okay, and that's what I want to say first. So the proof of star is more complicated than the one of proposition 45. That was this proposition which we started in the last semester. Since we need the asymptotics of psi n square root n e divided by alpha square root n rho of e. So rho of e is again the semicircle. For e non-equal to 0 or different from 0. And I think the psi n I defined last time, correct me if I'm mistaken. But that was essentially a rescaled version of this Hermite polynomial, so that was the main, that was the important term. And well, if you continue what we did last time here with the Fourier transform, then you will end up with the following. So that means we need the asymptotics of the integral IXC to the n e to the IXC square root n e plus alpha square root n rho of e e to the I c squared dxc. And yeah, last time we had this parameter small n, which was a capital N minus L, and now I want to take it L to be little l to be 0. So I take this for simplicity, because here you will already see the difficulty and now you see before e was equal to 0. So essentially this had one scaling, so this was the only term here, and well, we could just, well, in the end we saw that this would not matter, but now we have here this big term with the square root ne, and now this starts making troubles, and we in particular have to track well, how this evolves for large n, and the problem here is that this comes with a complex coefficient because we have IXCE in front of this square root n here. So let me rewrite it a bit in the form we had last time. So this is equal if we just change the coordinates again, so that the square root n we replace xi by square root n times xi, so we get another n here, and then it looks as follows. So it's n to the 1/2 n to the n over 2 plus 1/2 I to the n, and then xi I xi e. Maybe in this form one sees it even better. What's the difference to the last time? And then we have another factor here, rho alpha divided by rho of e dxc. So that's n independent, so that's what we had as a g last time. And but here now we have the problem that here we have also a complex phase in the we have a phase in this f, which we had last time, which we had to analyze in the large n regime, and that will make troubles. We need asymptotics of this integral. I want to introduce the same notation as last time. So, the g is obvious and the f is also obvious. It's very similar up to what we had last time, but there's this phase, and this makes the life much more complicated. Okay. And now this Laplace method we can no longer apply because of the following. The main point will be that for this Laplace method, as we will see in the exercises today, one essentially wrote this f as an exponential of some exponent, and then one had to analyze the maxima of this exponent. But now you have a complex exponent, so you will always have saddle. Whenever you look at the critical point, then you will have saddle points. So there's one direction where your thing will actually blow up compared to the saddle point, and there's one direction where it decreases, and you always want to pick this direction where it decreases and where it's stable. And this you can actually do by transforming the contour. But that's of course quite non-trivial. So Laplace is no longer applicable, because in some sense, the f has a complex exponent. So we need a generalization of Laplace method. We need its generalization. For complex exponents, and this is called the saddle point method, or method of steepest descent. And that works in the following situation. So consider the same type of integral as we had in the Laplace method. But now the f and g are holomorphic. So in particular complex valued. What's phi and g holomorphic? And yeah, of course, I want them to be complex valued on the real line. Otherwise, one can still go back to this. One can still go back to the Laplace method, and then one has the following. So one is still interested in the critical points. Well, there might be one or more. So yeah, that's where the complex derivative of phi vanishes. And then around this, you can still use the Taylor expansion. Well, any holomorphic function has a series expansion, and this tells me that the first term vanishes. So around this point, we have that phi of xi looks as follows. So it's phi of xi0 at the critical point, and then the so the first order vanishes, and the second order looks as follows. And then, well, there are higher order terms, but I just want to explain it heuristically, so I just want to use this approximation. And now I want to call these shifted coordinates z, and write and introduce x and y as its real and imaginary part. And then if you compute this z squared, then you see that you have a saddle point. So it's x squared minus y squared plus 2i xy. And 0 is a saddle point of each of the real part and of the imaginary part. Right. Or here you have one direction where well, if you take x0 and you vary y, then you have something which is decreasing, and if you keep y0 and x and vary x, then you have something increasing in both directions, and the same, or you can play something similar here. And well, you can, for example, take both of them with a negative sign. And if well, if both of them have the same sign, then it's increasing, and if both of them have the opposite signs, then it's decreasing. So there's really a saddle point of both of them. So if your integral doesn't go, so to say, through the doesn't go through this critical point in the right direction, then you will have some very big terms there. But on the other hand, because your functions are holomorphic, you can choose your contour, right? By Cauchy's theorem, you can just deform the integration contour, and that's what we want to do. So first, I should maybe remark that from this you see that each critical point is a saddle point. And because we assumed that the phi and the g are holomorphic, we can apply Cauchy's theorem and deform the contour, which was so far quite trivial. It just said that the xi has to lie in R. And now we have have a new contour which I want to call gamma of t. That passes through my critical point C0 in the direction of steepest descent. So that's why that is the good direction, and that's where the method gets its name from. Steepest descent, so that the phase is stationary, so the phase of this phi, so the imaginary part of the phi. And why do we want it to be stationary? Well, if it's non-stationary, then you integrate something which is oscillating. When you send n to infinity, then it will oscillate quite rapidly. And that means there are certain cancellations which are, of course, hard to control. And if we deform the contour in such a way that it becomes stationary, then such a cancellation cannot occur. So, so that helps us to control these cancellations and kind of transform it in a way where we can control or compute it. Okay. And now I want to be a bit more precise about how to choose this gamma of t. Well, anyways, I will only choose it very locally around this C0, so I can, in fact, just choose it linear to be linear or affine linear around t equal to 0, and I take a complex slope omega, and then I can compute the phi along my contour. So this is, well, not surprisingly, constant term plus, and then I have an a. So this coefficient here I want to call a. And then I have an omega squared t squared, right? Then what does this do? Well, you subtract the C0, and then you take the square of these things. So that's what you end up with. And now you compute the phase, and or you choose your omega such that the phase does not change. So choose the direction omega in S1 such that the following hold. Well, so t is real, and I will exponentiate the phi here. So what I will end up with is e to the phi gamma of t will be e to the value at the critical point times e to the a omega squared t squared. So this behaves like a Gaussian, and if this coefficient here is negative, then I have decay in both directions, and that's somewhat what we want. So what we will choose the omega in such a way that omega times a times omega squared is real and is in particular smaller than 0. And this I will call minus b. Of course, that's not really unique, but we can always find a complex number of this type. And then we can compute the phase, which is determined by the imaginary part of the phi of gamma t. That's the imaginary part of the value in the critical point plus a omega squared t squared. But now this whole guy here is real, so the phase will be stationary and just agree with the phase in the critical point. So the phase, yeah, well, maybe I can squeeze it in here, is stationary. And now we can also compute the real part. And as you know, if you compute the real part of the argument of an exponential, then this determines the modulus. And now we will see that the real part is negative, so in both directions. So when t gets bigger than 0 or smaller than 0, we have some decay. So the other thing is to compute the real part of phi of gamma of t. This is the real part. Same computation as before. Minus b t squared. And then remember or recall that that b is positive in the way we chose it. So here we really have the Gaussian decay away from t equal to 0. So if I now just look at the integral where around t equal to 0, then it looks again like something of the Laplace type, but now I have a complex coefficient, but that doesn't really matter. But apart from that, I really have what I expected. So now everything is a real integral, just with a complex coefficient. But for that, we can again use the Laplace method. So complex coefficient is not a problem. But it's a problem if this comes in a non-trivial with a non-trivial t dependence. Okay, and then that means we can apply Laplace method. Okay. So in some sense, what's happened now? So if this is my real line, then what we and maybe here I have this critical point c0. Then what we did is we chose some kind of different contour gamma of t to get through this critical point in such a way that we have these decay properties, so that we can locally use the Laplace method. So in some interval here we can use the Laplace method, but then we have to continue this here in some way. So maybe I can insert here that this is now a small regime where we can apply the Laplace method. So this contribution here we can control. But then what you have to do is you have to make sure that these contributions here are not too large. You have to control them, and yeah, this one has to do by hand. There's no general machinery to do that, and that's the hard part. So if you understand the critical points and the directions of the saddle, the directions of the steepest descent in these critical points, then you have somehow a guess for your integral by applying this Laplace method. But then you still need to control the error terms in some sense, and that's the hard part. That somewhat can be very technical. So away from t equal to 0, the integral has to be estimated by hand. So yeah, and there you have to be smart and choose your contour cleverly, in particular by choosing the contour appropriately. And yeah, this can be very hard. Yeah, in particular, I don't want to invest more time into this, and hope I gave you some idea of this deepest descent method, but this we will not pursue here. And well, I guess we have there are books where you can look this up if you're interested. And I guess this book by Anderson, Giuni, and Saituni explains this in detail. And yeah, I think this was it. And yeah, we will probably see some homework problem where one can apply this machinery that we've seen here to, in some easier case, to the circular unitary ensemble. There one can also follow this approach with the orthogonal polynomials, and then this kind of Laplace analysis. But everything is much simpler, and then one gets the same result. One also gets the sine kernel. Okay, and then what I want to continue with now is well, to give you some introduction into what we want to do for the rest of the semester, and then slowly start with the first method we want to use to prove universality. Is there any questions about what I've shown to you now? I guess that would be a good point. And if not, then okay, then I'll just start with the new things. And to motivate a bit, first of all, I guess still not so clear what universality means, so I will give some kind of informal definition. Of course, it's somehow it's not a fixed concept, so it's more like a philosophy of what one expects in many situations, and what has been verified in many cases from many ensembles and in statistics. But of course, there's no kind of general definition which covers all of the cases. So yeah, maybe now is in some sense the real start of this course. Okay, and yeah, so I will start with some introduction. And yes, I already indicated last time, so the main topic of this course, as the title already suggested, is the universality phenomenon in random matrix theory. So yeah, as I said, what is the idea of philosophy behind this? The idea is somehow that, and it has been seen in many cases, so microscopic statistics, so that goes into the direction of what I explained to you last time, that one looks at the scale of local eigenvalue fluctuations, and this seems to be around this one seems to have very robust properties of a random matrix, and you should always think of a Wigner random matrix, but it also holds in more generality for other ensembles and also for non-Hermitian random matrices, of course, with the appropriate changes. Should not depend on precise properties of the matrix. So that's distribution and distribution of individual entries or things like that, but only on the basic symmetry type of the matrix. And yeah, as we've also done in the first semester, we always look in the regime when the matrix size becomes large, so when its size becomes large. Okay, so I think there are a few words which might need some extra explanation. I've already said it in between. So microscopic statistics, so that's what I mean with if you look locally, you try to understand some local statistics of eigenvalues in the neighborhood of a special point. Then precise properties, yeah, you should maybe think of having different distributions for the entries. So what we've discussed so far was the k-point correlation function. If you rescaled it properly, then at least in the Gaussian case, you could see some limiting behavior. And but now it is the question: what happens if I don't have Gaussian, but maybe something which is close to a Gaussian or something of that type? And then the other things are then there's this basic symmetry type. And what do I mean with that? So it's so far we've looked at the Gaussian unitary ensemble, and actually it turns out that with more work you can also do the same computation that we've seen for the Gaussian orthogonal ensemble, but then you will get a different limit. So then, and that means that that's because they have different symmetry type. So maybe let me give some explanations on the terms I used here, and then some rule of thumb, which is what you should have in mind. So microscopic, well, as I've said and used last time, so it's on the scale of typical eigenvalue spacing. That's one of the things I wanted to explain. Then there is the precise properties. Yeah, well, there it's maybe good to think of the distribution of the matrix entries. So yeah, not having Gaussian, but something else, Bernoulli or something like this. And then there's this basic symmetry type. So yeah, you can think of having a real matrix which is symmetric. That's the standard example. Here's the Gaussian orthogonal ensemble. So it has real Gaussian entries and is Hermitian. So because it's real, then it's real symmetric. Maybe versus complex Hermitian. Okay, so these are maybe the explanation for the three most vague terms in this idea in philosophy. And then in particular in the view of this last part, the role of thumb, which you should have in mind, is that if I have a real symmetric, and then yeah, well, maybe Wigner matrix, but actually it's turned out that this is true in much more generality. But I don't want to go into the details now, here. So that means that I have a real n times n matrix which agrees with its transposed. Then if you want to understand the microscopic statistics of such a random matrix, then you should think of the analogous statistics in the Gaussian orthogonal ensemble. And the same holds true for complex Hermitian matrices. So in the matrix. So yeah, well, here it's a bit more complicated to define this. So in some sense, you should think of something which is maybe truly complex. And then this corresponds to the Gaussian unitary ensemble. Okay. And so now I want to give you some examples where one. So of course this is just the role of sum. So there are of course certain examples where this is not true, and then if you look at the, say, in some sense wrong statistics for the wrong type of matrix, then this is not correct, and you also need to find the right analogon here. So sometimes it's not immediately obvious, or it's natural, but then one might there might be some confusion what's the right thing to compare it with in the Gaussian case. And now I want to give you some examples of statistics where one can see or where one can prove universality. Unfortunately, we will not have time to treat all of them in this course, but I guess it's still interesting to see how far this concept can be pushed. Different statistics. Also in the matrix. Well, let's maybe restrict to the Wigner case. Wigner matrix showing universality. So the first one which I want to mention is what we've in some sense already seen at least in the case of the Gaussian, in the case of the GUE. So k-point correlation function in the bulk. So I guess bulk we have not really defined yet. I will do it now. So centered. Yeah, maybe I should also say entry scaled. Around E in -2, 2. So of course the picture you should have in mind this is always the semicircle. So in some sense this here is the edge regime. Then what's in between -2 and 2 is the bulk, and then around 2 we again have the edge regime. And yeah, so the k-point correlation function where you see the sign kernel is if you look in the bulk. So for the E being strictly away from -2 and 2, you see the sign kernel statistics if you have a complex Hermitian Wigner matrix, and but you can do the same at the edge. So that's maybe C. Well, there will be a B in between, but maybe it's now interesting to say that of course one can do the same thing at the edge, correlation function at edge. So that's when E is ±2. So then you can do the same scaling. It's just that you will see another kernel, which is the airy kernel. And but what one can also do, what is maybe more direct, is one can look at the distribution of largest eigenvalue. So if I look at the largest eigenvalue, then we have seen, it follows from the eigenvalue rigidity, which I'll actually recall a bit later today, but we've seen it last semester, that the largest eigenvalue actually converges to 2. And we also had a very sharp estimate on the size of the fluctuation, namely if I recall the eigenvalue rigidity, then what we proved there is that this here is stochastically dominated by n to the minus 2/3. So if we assume that the n to the minus 2/3 is optimal, then one would in some sense expect that if I subtract from the largest eigenvalue 2, and then I multiply it with n to the 2/3, then I get some order 1 fluctuation, right? That would somehow mean that this is in some sense optimal. Of course, then these n to the epsilon factors are not really there. And that's actually true, namely if you look at the probability of this, that this here is smaller than s, then this converges to random variable. So maybe I call it t of s, and this is an order 1, a non-trivial order 1 guy. This is follows the Tracy-Widom distribution, this is the distribution function of the Tracy-Widom. So that's another thing you can look at. So what happens here at the largest eigenvalue, and then for this for what I just erased, so the eigenvalue rigidity, we also had a more general form, namely we knew that we proved that lambda I minus gamma I is stochastically dominated, and then there was some kind of complicated, bit complicated formula to the minus 1/3, and yeah, maybe I should define the gamma I. So these were these quantiles. So gamma I of 2, if I integrate it against the semicircle, then this should be I, and I think there was some normalization. Yeah. Okay, so that means that the eigenvalue, the ith eigenvalue, will with very high probability be, well, actually when you're away from the edges, this is 1 over n to some deterministic location which will change with n, but this holds true now for all large n. And in a similar spirit to the distribution of the largest eigenvalue, one can also look at the distributions of the ith eigenvalue when you subtract the gamma I. So maybe part D, fluctuation of lambda I around gamma I. And well, maybe I want to have some condition here, still heuristic, but so you should think of the I being away from 0 and away from n in this sense. Well, okay, so for some small c. And then in this case, actually, you will not have the Tracy-Widom fluctuation. That's really the right fluctuation at the edge. And in the bulk, you will have Gaussian fluctuations. And then you can check that if the I is in between here, then this here is 1 over n. And yeah, if you rescale this difference by n, and there's some other factor, or if you scale it by n, then you will get the Gaussian distribution here that one can also see, and then maybe something else, and then I'll stop with these examples. One can also look at the gap distribution. So that's lambda I plus 1 minus lambda I. And that's actually the first thing which Wigner was interested in, and maybe we mentioned it in the first course. So Wigner started with this kind of analysis of the eigenvalues of large random matrices, and what he was interested in was these kind of differences, so the gap distribution. And why was he interested into that? Well, he came from the physics side, and he wanted to understand quantum mechanical systems or heavy atomic nuclei. And then I guess you've all seen a bit of quantum mechanics. So then, of course, the eigenvalue, then you look at the Hamiltonian, which describes the energies of this system, and the energies are given by the eigenvalues. So if you take these differences, then these are the transition energies. So if you want to go from energy level to the other. And what Wigner suspected that these differences, they're actually independent of the precise properties of the model, but just depend on this kind of basic symmetry type, which I was talking about before. So that's actually, so he already had the vision for this universality ideas. But then it took much longer to prove these kind of universality statements in this vein. So all of what I told you here has actually been proven in quite generality, and there's been more, but I don't want to go into the details here. And yeah, unfortunately for this class, we will have to restrict ourselves a little bit. Yeah, because the proofs are actually a bit, well, they have some very interesting ideas, but they take a while to be explained. And in this course, I will focus maybe on A and B. But if you're interested, I can of course give you references to literature. And yeah, we will also restrict to maybe not all Wigner matrices, but certain classes of Wigner matrices. And yeah, maybe this is a good time for a break. And then after the break, I want to at least mention a few methods which one can use to prove such kind of statements. So the universality of these kind of statistics, and then give some idea, and then maybe recall a bit of the local law, and then yeah, we will see how far we will get, and then we continue. Yeah, maybe at 20 past. Okay, then I guess we can continue. And so yeah, now I gave you some ideas of what kind of statistics one wants to analyze, and then maybe it's also insightful to give you some at least feeling of what kind of methods one can use. And yeah, the first method, which we'll also use in this course, and that's called green function comparison. And there one usually has some assumption on the moments of your entries of the matrix. Okay, so what does that mean? So well, green function is just another word for the resolvent, and what we've seen last semester in a few examples is that the green function carries many information, or essentially all information about the spectrum of your random matrix, or of a Emission matrix, and in many cases it's easier to deal with the green function first and then conclude something, for example, about the eigenvalues, and that's also correct in this case. And what's the basic idea here is that if the moments of, entries of two matrices of, say, H and H prime match up to a certain order, match up to some order, then one can conclude from this, and then, well, that's a quite non-trivial statement, but that the distributions of two resolvents of the two resolvents of H and H prime are close. It's a quotation mark. This don't give any precise definition for this now. And you remember that last semester we were looking at these kind of local laws, and then the threshold in some sense was when the imaginary part of Z became smaller than 1 over n, or came close to 1 over n, because that's the eigenvalue, that's the difference when you start seeing, that's the threshold when you start seeing individual eigenvalues from this kind of resolvent. But now if you have this kind of assumption on the moments, then you can even push this further, and you can go down to the imaginary part being slightly smaller. So now I have minus 1 minus epsilon. So last semester for the local law we had plus epsilon, so that was above eigenvalue spacing, and now we can go slightly below the eigenvalue spacing, and then we can understand the local eigenvalue distribution. And so from this we would then get that the local eigenvalue distributions are close. Again, without making it precise. So in the end, what you will do is that you will look at certain moments or mixed moments of this. No, you will look at moments of the. You will compare moments of the resolvent, and then you can say something about the moments of the eigen, or about these k-point correlation functions, and that's what I mean with local eigenvalue distributions here. So that's one method, just summed up in 3 lines, but the proof will be the actual proofs will be a bit longer. Then another method goes under the name of Dyson-Brownian motion. Also here I want to summarize the idea in a very short, just in one formula in 2 lines of text. So we look at the following differential equation, which is a stochastic differential equation because it has a term that comes from Brownian motion, and actually it's a system. So now the I runs from 1 to n, and these are well, maybe b1 up to bn are independent Brownian motions. I hope you all know what a Brownian motion is, but if not, we can recall that before we come to that. And yeah, so here you have a system of n coupled equations with some drift, with some drift term and some probabilistic term. And the interesting thing is, so in some sense you can imagine that this adds some kind of Gaussianity to your system, in particular because this is a counterpart on the level of the matrix. And the way this method here works is that you can choose your initial condition, choose initial condition lambda I of t equal to 0 as eigenvalues of a Wigner matrix. And then if you let the time run for a little while, then you can actually, then it's much easier to prove that you have the same statistics as in the Gaussian case. And this already happens for a very short time. And then in some sense one can remove this time this time again. So lambda E at this local eigenstatistics have local statistics of eigenvalues of Gaussian ensembles. Well, this was maybe not good. Yeah, let me write the rest on another board. After a short time, so it will, in the bulk, it will actually be just a little bit longer than time 1 over n. And then that will enable you to compare it with the original matrix again. And so we'll have of Gaussian ensembles after a short time. And then you can compare lambda I of this after a short time. Maybe I call this T star. This may be clearer what I meant. And then you can compare the eigenvalues at the time T star and the original eigenvalues, and then you can conclude that you have universality. So that's the second method. We will actually in this course see both of these methods, and in both cases the local law will be an important ingredient to analyze this method. Let me just mention a third method, which is in some sense a generalization of what we've seen before today. So that's the saddle point method. So that's actually, one can extend this method I've indicated today to use for general E in the Gaussian unitary case. One can also generalize it quite a bit, or for certain types of random matrices. It's maybe not so suitable for Wigner matrices, but if you go to this invariant ensembles, which we've seen briefly in the last semester's course, then this saddle point method is quite powerful. But I don't want to say much more about this, because in this course we will restrict to 1 and 2, and well, in both cases the results from last semester will be helpful. In particular, the local law. So just to recall, so we had two main results in the last semester. So that was the local law. In some sense, the connection to this year's course is that this will be an input for both of these methods, 1 and 2. And then the other thing was that we could prove that if I take the k-point correlation function of GUE, say, and I rescale it appropriately, alpha 1 rho E times n, and alpha k rho of E times n. Then this converges to the sign kernel. And what will be the connection here to this course? Well, what we'll actually prove, that we'll now do in the next lectures, is to prove that this k-point correlation function, if I don't have GE here, but another Wigner matrix, and then it has to be a complex Hermitian Wigner matrix, then that will be close to the GUE, to the k-point correlation function of the GUE. So then, since we already know this statement, then we will know that for all matrices where the k-point correlation function is close to the k-point correlation function of the GUE, we will also have the sign kernel statistics for large n here. And the same holds true also for the Gaussian orthogonal case. So maybe as a last appetizer before we come to the real mathematical part of this second lecture, I want to just formulate an informal version of this first main result, which we will prove in the next lectures. One of the main results of this course will be the following. I want to state it as an informal version. In particular, I don't want to specify the assumptions I have on, and not the sense of convergence, but so under some assumptions on H, I have the following statement. So I look at the k-point correlation function of this H, and I subtract the k-point correlation function, say, of GOE, and then I will be able to prove that this converges to 0 when n goes to infinity, in certain sense. If H is real symmetric, and the same kind of statement I have if the H is complex Hermitian, except that then I will converge to the k-point correlation function of the GUE. Of course, this is not a precise statement. I was not explicit about the assumptions here. In fact, we will start with some moment matching assumptions, and also the sense of convergence will have to be made precise. But that's the idea. And yeah, as I said, we will first use this method 1, and then the local law will be an important input. And that's the reason why I want to start with a short reminder on the local law and eigenvalue rigidity now in a section 1. And we also need to extend the local law a little bit. I will explain this now. So local law and eigenvalue rigidity for Wigner matrices. And yeah, this will now be a version which we will use throughout the semester. Maybe I first recall some notation. I guess you're all familiar with that, and if there's something unclear, just ask me. So as usual, we work with a Hermitian matrix. now either real symmetric or complex Hermitian, then we define the resolvent or green function. This we've all seen last semester. I just want to introduce the most basic things, and in case something was forgotten about the semester break, while the semester break. So, and here this is always invertible if I have a complex Z with positive imaginary part. And then the other object which we looked at was the little g, which is the normalized trace of G. And in fact, that was the small computation showed that this is the Stochastic transform of the empirical spectral measure. Okay, and so that was the uniform measure, uniform probability measure on the spectrum, and the important thing was that in order to prove, well, it's called local semicircle law. So somehow the semicircle should appear, and the semicircle appears through its Stochastic transform that we denoted by little m. So little m was, yeah, well, let me write like this, 1 over x minus z rho of x dx. So that was Wigner's semicircle. Maybe to be very explicit, one can compute it, and yeah, so this is the Stochastic transform. Of the semicircle. And now to state the local law, we use this following error parameter. Which is also given in terms of the Stochastic transform of the semicircle. So I have it depends on z, it's non-random, but it depends on z and on n. Via this formula. Yeah, just recall that eta is always the imaginary part of z, which gives you the spectral resolution. And then the theorem 1, so use slightly different notation than last semester. That's the local semicircle law. So H is a Wigner matrix. So what were the properties of a Wigner matrix? Well, it was centered. Then the variances of all entries were 1 over n up to a small error term. And the most important thing was, of course, that it's a Hermitian matrix, and the upper triangle consists of independent entries. And then we had some moment conditions. So I don't want to write down the definition again. If I can refer you to the last semester's lecture, or give you also some literature if you need it. And then we always had a tau, which defined our spectral domain. And now we have a slightly bigger spectral domain, namely where the S star is defined as follows. I have an E plus I eta. So the E is real and in absolute value smaller than 1 over tau. And the eta can now go all the way down to 0. And for technical reasons, it will be easier to formulate the local law on this domain. So with this spectral domain, we have the following results. We have that the little g is equal to m of z up to an error term of order 1 over n eta. And the entries of my resolvent are well approximated by m if you look at the diagonal entry, and by zero otherwise, up to an error term which is described by this error parameter phi, and this holds uniformly for z in S star and all I and j from 1 up to n. Okay, so maybe now you might ask, well, why can we suddenly now drop our lower bound on eta? Last semester I was always, it was always very important to have an n to the minus 1 plus epsilon here as a lower bound. Well, the point comes from the fact that this error term starts to be, starts to lose its effectiveness as soon as the eta becomes smaller than 1 over n. But nevertheless, such a bound is still very helpful in certain technical steps to control, well, the little g or the big G, even when the eta goes down. I mean, sometimes you multiply it. You multiply such a guy with an eta, then of course everything is much better. And you might remember that last semester when we proved the semicircle law on small scales, we used this Heffler-Chestran formula, and there we already used implicitly some kind of extension of this type, just because it will come up a few times this semester. I wanted to formulate it explicitly, and maybe also say a few words about the proof. We basically did everything already last semester, but it does not harm, I guess, to say a bit about it. And the main tool there will be a monotonicity estimate on the resolvent, or the maximum norm of the resolvent. So just to compare it to what we've done last semester, so from theorem 11 in last semester's course, we know this theorem 1.1 for z in S. That means that the eta had to be bigger than, like this. Eta is bigger than minus 1 n to the minus 1 plus tau. And now we will use this theorem and then extend it to this new spectral domain S star, and we will use the following notation. I introduce gamma of z, which is the maximum norm, entry-wise maximum norm of the resolvent, and we have the following property, lemma 1.2. Whenever I have an m, real number m, which is bigger than 1, an e and an eta bigger than 0, we have the following: gamma of e plus I eta over m is smaller than m times gamma e plus I eta. And when you think about it for a minute, then you will realize that this is in some sense a monotonicity property, namely if you multiply this here by the imaginary part of z, then this function will be monotonically decreasing. And the fact that there's an m here just means that it's just a reformulation of this. And the proof we actually had once on the homework, so I will not go into the details here. You can also find it on the in the lecture notes of Benaich, George, and Knowles. So yeah, we've done it in the homework, and from this it's very easy to prove theorem 1.1. So yeah, we just start with the general E, and we can now assume that the eta lies between 0 and n to the minus 1 plus tau, right? And we will prove the second part first. And this goes as follows. It's really just want to have some control on the entries. And actually the m doesn't play a role anymore because it starts being much smaller than this. M of e plus I eta delta ij. So that's smaller than, because the m is bounded, the gamma of e plus I eta plus some constant c. Yeah, so as the m is bounded, well, that's what we proved in one of the lemmas last semester. I didn't look up the number, but I'm sure you will find it easily. Then we can use the monotonicity of this gamma. So because now I want to replace this eta by an n to the minus 1 plus tau, because then I can use the old lemma, the version of the local law that we've already proved when the z is in S. So by choosing the m correctly, I get this thing here, gamma of e plus I n to the minus 1 plus tau plus c. Let's see how long I can keep the local law. But now I know that the gamma is bounded on this value, so it's stochastically dominated when I use theorem 11 from the first course by n to the tau divided by n to the n times eta. And also the c, well, the c is just a constant, but this here is stochastically bigger than a constant, so I can forget about this. And now I can easily estimate the things, and I get that this is n to smaller than n to the 2 tau c of I eta. And here I used that the psi is bigger than n to the minus tau. Okay, and now I can use this usual trick that we used many times with the stochastic domination. So now the tau was arbitrary. So I can incorporate it into the stochastic combination. So g ij of z minus m of z delta ij is bigger than psi of z uniformly. And the z is in S star. And that comes from the upper bound on eta and from the definition of psi, right? So there's a, well, there was in particular this term, is that the correct one? Yes, so now I have an upper bound on eta, right? So that gives me a lower bound, I have an upper bound on eta that gives me a lower bound on this, and the upper bound is, right, the eta had this condition here. The eta was small. So times this times 1 minus 1 plus tau, right? That's the second term in the definition of the psi.
But here we have eta.
You don't believe this, or you don't know how it helps, or?
I don't see how it helps.
I mean, I have a. Did I do it wrong?
If you write n to the power of tau, then it is just the fact that psi is at least 1 over n.
Yes. Okay. What did I do there? No, wait, that was overcomplicating things. I think this is not there, and this is, yeah, you're right. I mean, the 1 over n eta is smaller than the psi, right? Yeah, you're right. I don't know what I did there. Thanks. So the psi is the sum of something like this and some other positive terms, so I can just incorporate this here. Okay, perfect. Thanks a lot. Yes, so this proves the first part, and the second part goes very analogously. So when I subtract the g and the m, I can use the same as before, and because the g is the normalized trace, I can estimate it by gamma of c. And then I can do the same thing as before. So this is n over tau n eta gamma of this thing here, and then I can again use the local law and estimate everything as before. So this is n to the tau 1 over n eta, and now we're even faster because that's really the term we want. The tau was again arbitrary. So this implies the first part, and okay, so that was the proof of the local law. And now I also want to recall this eigenvalue rigidity, which I already mentioned. Wigner matrix I will still need. Because that will be another important point. So we also recall 1.3, just to have a fixed reference and not having to go back to the last semester all the time. So for a Wigner matrix, H the ordered eigenvalues. I ordered them in decreasing order, I think. No, increasing. The ordered eigenvalues satisfy. So I have the lambda I minus gamma I is stochastically dominated by n to the minus 2/3, and then times I maximum, this should have maybe said before, n to the n plus 1 minus I to the minus 1/3. So yeah, this is the maximum. And the gamma i's are the typical locations. So gamma I is the typical location of lambda I. Defined by the following formula. So it just, if the lambda i's would be perfectly distributed according to the semicircle, then you would expect that these are the quantiles. So this is I minus 1/2. Okay. So yeah, what does that mean? So yeah, as I said, the gamma i's are the quantiles of the semicircle distribution. You know that on the global scale, the eigenvalues, and even on the local scales, the eigenvalues are distributed according to the gamma, and this means that the gamma is the ith eigenvalue is very close to gamma I. And you know here that at the edge, this term vanishes or becomes 1. So then the spacing is n to the minus 2/3, and well, inside the bulk, this is n to the minus 1/3. So the difference is 1 over n. Okay? And yeah, if you don't remember the proof or you want to look it up again, then just give you a reference. It was theorem 30, and I can also give you also looked up which lecture we had it. So if you want to refresh your knowledge, then yeah, the proof is theorem 30 in the first course. And well, yeah, see lecture of the first course. I think it was on November 12th. You know that you can look on all of those on YouTube, and it was, I think the explanation started after minute 53. Okay, so I guess that was some introduction into what we want to do with the universality this semester. Yeah, then in the end, I recalled the main results we will use from the last semester, so that where the local law extended all the way to the imaginary part being 0, and then also the eigenvalue rigidity, which will in particular be important when we look at the edge eigenvalue and see the universality in this Tracy-Widom sense. And then next time I will introduce these moment matching conditions more precisely, and we will state and maybe start the proof of the bulk universality, so the universality of the local k-point correlation function, if we have this moment matching condition. And there we will use the screen function comparison result. And maybe if you already seen the Lindenberg's proof of the central limit theorem, the proof will in some sense mimic and extend this result. Okay, and then that's it for today, and then see you later in the exercises and then also next week.